This is the review on electromagnetic radiation or light and optics. First of all, there are some characteristics of all waves, and light is a wave. They reflect, refract, they travel in a straight line, they diffract, and they interfere. When we did waves in the last unit, we talked about there were two main types, electromagnetic and mechanical. We talked about mechanical in that unit. Now we're talking about electromagnetic. The biggest difference is that electromagnetic waves do not require a medium to travel through. Electromagnetic radiation is transverse, not longitudinal. And we call it electromagnetic because it has an electric component and a magnetic component. There are several models of light, like ways we can picture light or think of light. The ray model, wave model, and particle model. We will use the ray model quite a bit. It's easy to draw. It works because light travels in a straight line, and so we use these straight line arrows to show the direction that light's traveling. The wave model, this would be like crests and troughs traveling, and they would be traveling in this direction. It helps us when we talk about wavelength changing and that kind of thing. The particle model is required to explain some phenomena like the double slit diffraction experiment that we'll talk about at the very end of this presentation. The particles are called photons. And actually, light is both a particle and a wave. It's called the dual nature of light. I like to say it's like Batman and Bruce Wayne. They have a dual nature. Sometimes you see Bruce Wayne characteristics being exhibited. Sometimes you see Batman characteristics being exhibited, but it's always Bruce Wayne and Batman all at the same time. Light is a particle and a wave. These are examples of the ray model. See, the wave model in this example is a little bit awkward, but just a nice clean ray diagram looks really nice. This is an example of reflection. The incident ray bounces off and you get the straight reflected ray. And these are just some more examples of the ray model of light. The speed of light is 3 × 10⁸ meters per second, and you need to know that value. For any wave, oh, wait a minute. So notice it's really fast. So why do you, is it clear now why you see the lightning before you hear thunder? Well, we're comparing a speed of sound of 343 meters per second with the speed of light 3 × 10⁸ meters per second. The light travels much faster. We already know that for any wave, the velocity is frequency times wavelength. Now we use c because it's the speed of light instead of v. And so given frequency of light, you should be able to calculate wavelength. Frequency would be equal to c over lambda, and you should be able to find the wavelength. Wavelength would be c over frequency. The electromagnetic spectrum. So light can be very long wavelength, very short wavelength. It can be very high frequency at this end, high frequency, or it can be very low frequency. Notice long wavelength is what you get when you have low frequency, and this is also low energy. Energy is directly proportional to frequency in light, and this would be high frequency and high energy at this end. Short wavelength. You need to know the order of the radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. The gamma rays are the highest energy, shortest wavelength, highest frequency, and radio is the longest wavelength, lowest frequency, lowest energy. The visible spectrum is here in the middle. And remember Roy G. Biv, I'm sure you've had that. The order of the colors, red, orange, yellow, green, blue, and then the purples are at the end. I think they technically dropped the indigo. So the special thing about that is our eyes are sensitive to those frequencies of light, and so we can see them. You can calculate the energy of a photon very easily. Energy equals Planck's constant times frequency. Planck's constant is 6.62 × 10⁻34. When light hits a surface, various things can happen. It can reflect. It can be absorbed by that surface, or it can be transmitted through that surface. And if it's transmitted, it can be refracted if the speed changes. This slide is in here because there are some questions on quizzes and tests about what can happen when it hits a surface. And you need to know that it can reflect, it can be absorbed, or if transmitted, it can refract. Any of those things can happen when light is in an incident on a surface. The law of reflection says that the angle of incidence is equal to the angle of reflection. And when it talks about these angles, it's not the angle with the surface, it's the angle with a normal line. So this red line is the normal line. The incident angle is here, the reflected angle is there, and they are equal to each other. You get a regular reflection and can see images when the surface is regular, and so rays that come in parallel bounce out parallel to each other. You get a diffuse reflection when the surface is bumpy, and the rays that come in parallel, which was this and this and this, do not bounce out parallel, so your eyes don't see an image from those reflected rays. A plane mirror means a flat mirror, not an ordinary mirror, but a plane like in geometry plane. If we look at the characteristics, the image height versus the object height. Well, the object height is the height of the object, obviously, and the image height is the height of the image, and for a plane mirror, they are equal. Magnification, magnification is image height divided by object height, and for a plane mirror, it equals 1. The image and the object are the same size. The image distance is the distance from the mirror to the image, and the object distance is the distance from the mirror to the object. And for a plane mirror, they are equivalent. The image from a plane mirror is virtual, and what do we mean by that? If the image is back here behind the mirror, not on the object side, but behind the mirror, then it is a virtual image. This is even called the virtual side of a mirror, and this is the real side of a mirror. It is not created by light actually intersecting there. The light hits the mirror and it bounces off. The light never goes where that image is, and so it is a virtual image. We have curved mirrors. We have convex mirrors, which are the ones that kind of bulge out in the middle, and we have concave mirrors, and those are the ones that kind of go in the middle. Ray diagrams are helpful for locating images, but you don't have to draw 5 different rays. You really only have to draw 2. And the rays that you have to be able to draw are, let me pull up a tool that let me draw a straight line, are this one right here and this one right here. So I'll draw them over here from the object to the mirror parallel to this line called the principal axis. Remember, the line that goes to the center of the mirror is called the principal axis. This is the focal point. This is the center of curvature. It would be the radius of the circle that the mirror makes. The mirror is a sphere. And so if it hits this, the rule is it will be reflected through the focal point. And then the other ray that you draw is from the tip of the object through the focal point to the mirror, and it will be reflected parallel to the principal axis. Notice they are inverses of each other. If the incident ray is parallel to the principal axis, it will be reflected through the focal point. If the incident ray travels through the focal point, it will be reflected parallel to the principal axis. And where they intersect is the image, and you would draw that image from the principal axis down to that point of intersection. Okay? So you only need 2 rays to draw a ray diagram and locate an image and get an idea. Let's talk about what the stuff we know about this image because of what it looks like. It's a real image because it is on the object side. Remember, this is the real side, and behind the mirror is the virtual side. It's inverted. You can tell because it's upside down. It is actually reduced. It's smaller than the object. It's real, inverted, and reduced. Okay, so let's look at what other ray diagrams for. This is a concave mirror. For concave mirrors, depending on where the object is, the image looks very different. We're going to look at the different cases. And I'm going to draw some rays. If the object is inside the focal length, you can't draw the ray that goes through the focal length first because the focal length is behind the object. So you draw parallel to the principal axis and then reflected, through the focal length. And then you have to do the vertex ray, which is from your object to the point where the principal axis hits the mirror. And that's an easy one to draw because these two angles will be equal because of the law of reflection. But these rays diverge. Notice they're not parallel. They don't converge where the image should be. So you have to dot back, and where your eye, oops, I can't draw a curvy thing with this tool, but anyway, if you were back here looking, your eye would trace those things back to where it looks like they intersected, and the image is back there. That is a, hold on a second. Okay, I'm back. So if the object is inside the focal length, then you get an enlarged virtual image, virtual because it's back here way behind the mirror. It's upright as well. So if the object is at the focal point, you don't get an image because again, you can't draw the focal point ray because it's sitting on the focal point, so you have to draw the vertex ray. And they come out parallel, and they never intersect on either side of the mirror, and so there's no image. So in all of the other cases, the ray diagrams are very similar to each other, and you have the ray 1 that goes parallel to the principal axis and then through the focal point drawn. But I'll draw the second. If it goes through the focal point, it's reflected parallel to the principal axis, and where the rays intersect, you have your image. So I'll draw them on here, parallel to the principal axis, through the focal point, through the focal point, parallel to the principal axis. I kind of goofed on that one a little bit. And where the rays intersect, you have your image. So that's for concave lenses. For convex lenses, there's only one case. And now they've drawn 3, but the object just gets closer, but the ray diagram looks the same. So here's the tricky thing. If it's a convex mirror, the light does not reflect towards the focal point. It bounces away from the focal point, but still in a line with the focal point. And so you dot back and complete that connection with the focal point. The second ray, you aim it at the focal point, but it doesn't go through the mirror because it bounces off the mirror. So that's how you get the direction of this line, is through the focal point. You stop at the mirror, and it is reflected parallel to the principal axis. So same 2 rays, parallel to the principal axis, through the focal point, but now on the far side. Draw it towards the focal point on the far side, and it's reflected parallel to the principal axis, and you dot back, and where those 2 intersect, there you have your virtual, upright, reduced image. And it works the same for the others. Parallel to the principal axis, reflected away from the focal point, aim it towards the focal point on the far side, it hits the mirror and is reflected parallel to the principal axis, you dot back, and the image again is reduced, virtual, and upright. All virtual images are upright. All real images are inverted, upside down. Some sign things that you need to be aware of. The focal length, like when you plug it into the equation, that we'll do in just a minute, is positive if you have a concave mirror. It's negative. See, if the focal length is over here, it's a positive focal length. If the light comes this way and the focal length is over here, then it's a negative focal length. The image distance is positive if you have a real image. So this would be the positive image, the distance over here. And if the image is behind the mirror, you have a negative image distance. And the image height is positive if your image is upright, and it's negative if the image is upside down. So the thin lens equation that we need to use, I don't know why I didn't type it out, but 1 over f equals 1 over di plus 1 over do. 1 over the focal length is 1 over the image distance plus 1 over the object distance. Magnification is equal to the image height over the object height, which is also equal to negative image distance over object distance. Okay, so if we want to find the image distance, 1 over the image distance equals 1 over the focal length minus 1 over the object distance. So that's 1 over the focal length is 60, and the object distance is 75. So when you do that on your calculator, okay, I'm going to see if I can get my calculator. I'm having to use my phone, and my phone is misbehaving. Okay, I think I might be able to get it. Second. Okay, so 1 over 60 minus 1 over 75. And when you do that, you get 0.00, and it's 3 repeating, so lots of 3's. But that is not your image distance. That's 1 over your image distance. And you have to invert that, and you get an image distance of 300 centimeters, or 3 meters. So we've found the image distance, the image height. We use this relationship. And I'm going to solve for image height equals negative di over do times ho, and multiply both sides by ho. So that's negative 300 times the object height was 15, divided by the object distance, which was 75. So 300 times 15 divided by 75, I get negative 60. That negative sign means it's inverted, and that means it's real. And then magnification is image height over object height. So the image height is 300, and the object height, I'm sorry, that's the image distance. The image height was 60, negative 60, divided by the object height, which was 15, and so that's negative 4. So the negative means it's upside down, and the 4 means it's 4 times bigger, the image is 4 times bigger than the object. Okay, refraction happens when light bends, when it travels from one medium to another, and changes speed, speeds up or slows down. And this is an example of refraction. The light that has to travel through the water travels differently than the light that travels through the air because they travel at different speeds in those two different media. This is an example of refraction. This would be our incident ray coming in here, and this would be our refracted ray, and you can see it's bent. This is the normal line, normal to the surface. In this case, this is air, where light travels fast, and this is water, where light travels slower. And you can see that the light is bent what we call toward the normal line. So this light ray would have continued like in this direction, but that is bent toward the normal when it goes from a fast material to a slow material. If it came back out on this side, back into the air, we would see that it would be bent like this. We'd have to draw a normal line in, and it would be, the light would go like this if it were not refracted, but it's bent away from the normal if it goes from slow to fast. So fast to slow toward the normal, slow to fast away from the normal. The index of refraction is a number that is for a material, like for water or for glass or for air, and it is the ratio of how fast light travels in a vacuum to how fast light travels in your material. Can C ever be greater, can N ever be greater than 1? And no, it can't, because C is the fastest light can travel. So you're always going to have, that shouldn't be less than. Can it ever be less than 1? And no, it can't ever be less than 1, because the top number is always going to be bigger than the bottom number. C is always going to be 3 times 10 to the 8th, and the velocity in anything else, it's going to be slower. So like for glass, the index of refraction is usually around, 1.6, and for water, it's 1.32. So given this equation, if you are given any two of those three, you'll be given C, you know what that is. Given either index of refraction, you'll have to find velocity, or given velocity, you'll have to find index of refraction. This is Snell's law, and it's the relationship between the indices of refraction of two materials and the angles of incidence and refraction. This is the incident angle, theta 1, and this is the refracted angle, theta 2. So this is material 1 with index of refraction 1 and material 2 with index of refraction 2. So N1 sine theta 1 equals N2 sine theta 2. Light and air hits the surface of water at a 30-degree angle with the normal if N is water. For N for water is 1.33, find the angle of refraction. So I should say surface. Can you tell I did this fast? So N1 sine theta 1 equals N2 sine theta 2. And I want to find the angle of refraction, which is theta 2. So sine theta 2 equals n1 over n2 sine theta 1. And so that is n1, n for air is 1, n2 is 1.33, and sine of 30 equals the sine of theta 2. So let me get the calculator out, which is my phone, which is misbehaving. I'm going to pause this while I get my calculator going. Okay, so I'm calculating. Sine of 35 is 0.5. 0.5 divided by 1.33 is the sine of theta 2. And 0.5 divided by 1.33 is 0.3759. And then you have to use your inverse sine function. The sine to the minus 1 of 0.3759 is my angle, which is 22.1 degrees. So critical angle happens when light is going from a slow material into a fast material. It only works if it's going from the slow material, high index of refraction, to low index of refraction. And as this angle, the angle of incidence, gets bigger and bigger, at some point the light is refracted right along the surface and none leaves. And that happens at the critical angle. This is theta c, or the critical angle. Anything bigger than that, you have total internal reflection, where all the light comes back into the material. To calculate the critical angle, the sine of your critical angle is the ratio of the indices of refraction. N2, that'll be the low one, the faster material, so it'll be the low one over the higher one. So N2, second material, divided by N1, and do inverse sine, and you'll get the critical angle. There's a really cool video that I'm not going to take the time to show because this presentation's getting really long. Oh heck, let's watch it. Setting up, he's got a light box, and the light is coming through this material, and you can see the refraction happening at that point where the light leaves. And then when he moves it a little bit more, moves it a little bit more, moves it a little bit more, you can see some internal reflection happening here. And then at the magic angle, all of the light is internally reflected. So that didn't take very long. That was worth it. Okay, so that's total internal reflection. This is not in your content, but I thought you needed to know that rainbows happen because of refraction. You've got light coming from, it happens when the sun is behind you. It's supposed to be the sun. And you're here, and the rain is falling here. Then the light will come from behind you, hit raindrops, be refracted and reflected back to you, and you'll see color. You can see as the light enters, it splits into its component colors. As it leaves, it's split even more. And so from your eye, you'll see the red band up here, and you'll see a green band here, and you'll see a purple band there. And so the raindrops split the incident light into its component colors and makes a rainbow. There are two types of lenses: convex lenses, which are also called converging lenses, and concave lenses, which are also called diverging lenses. Remember, this is called the principal axis. We are going to do ray diagrams again. If light comes from infinitely far away in parallel lines, it will hit the focal point. Again, the thin lens equation, just like we've had before, the magnification that we've had before, and the same quantities that we've looked for before. Sign conventions: if you have a convex lens, focal length is positive, and the image, I guess that's the most important thing. Focal length is negative for a concave lens and positive for a convex lens. And the other things, the image distance can be positive or negative depending on where the image is. Focal length positive for converging, negative for diverging. Object distance is always positive. Image distance is positive if, now see, lenses light is transmitted, it goes through. So this is now the real side with a positive image distance, and this is now the virtual side with a negative image distance. So if your image is on the light on the far side of the lens, you'll have a positive image distance. The image is positive, image height is positive if the image is upright, it's negative if it's inverted. Magnification again is positive if the object is upright and negative if the object is inverted. So I have a 2.25 centimeter tall object, so that's object height placed 8.5 centimeters to the left of a convex lens, so this is object distance, and the focal length is 5.5. It's a convex lens, so it has a positive focal length. So 1 over f equals 1 over di plus 1 over do. And so 1 over di equals 1 over f minus 1 over do. So that's 1 over 5.5 minus 1 over 8.5. And remember, that's 1 over my image distance. Let's see if I can get the calculator up again. Yes, okay. So 5.5. 1 over minus 8.5. Okay, so I get that 1 over my image distance is 0.064. And then when I invert that, I get my image distance is 15.6 centimeters. So I've got the image position, where it is, and the image height. Remember that, just like we did before, is negative di over do times ho. So that's negative 0.064 divided by the object distance, which is 8.5, times the object height, which is 2.25. So 0.064 times 2.25 divided by 8.5. I get an image height of 0.02. Okay, that's really, really small. So let me pause. Hold on a second. Sorry. The pause button is very, very low. Okay, I found my mistake, and you probably did. You saw me do it. This is the image distance. I used that. So the image distance is negative. I'm going to have a negative 15.6 there. So 15.6 times 2.25 divided by 8.5. That's much better. The image height is 4.1 centimeters. Okay, sorry for the mistake. Ray diagrams, we're going to do the same two rays. For convex lens, the converging lenses, these are the 4 cases that you can have. I like to do the vertex ray for these. You can do the other one. I'll show you if you do. If you draw through the focal length where it hits the lens, it's refracted parallel to the principal axis. Notice that you get that intersection there. If you draw it through the focal length till it hits the lens, it'll be refracted parallel to the principal axis. But honestly, that one that goes through the center of curvature, that ray is not refracted, it goes straight, and that's the easiest ray to do. You get no image if the object is at the focal length, and you get enlarged virtual image if it's behind. You've got parallel to the principal axis, refracted through the focal length, and so you dot back from there. You've got your vertex ray, and you dot back from there, and you see your image is behind, on the light side of the lens, so it's a virtual image and it's enlarged. Concave are a little different, but you only have one case. And so you have the incident ray parallel to the principal axis. It is refracted away from the near focal length, and you dot back there. That's how you determine the direction. You lay a ruler down from the focal point, and where the lens starts, you draw the light ray. You have the vertex ray, which is the simplest to draw, and it would reflect back along itself. And then towards, this one was drawn towards the focal length. When it hits the lens, it's refracted parallel to the principal axis, and you dot back. So you get your real image with a positive image distance. It's reduced, and it's real. Sorry, virtual. Upright images are always virtual. Diffraction, we're getting close to the end. Diffraction happens when waves encounter an obstacle or a slit, and they bend around it. Instead of continuing straight on this side, they bend. This enables, like if you're talking in a room and there's a doorway, the sound waves, instead of staying limited, like, so we changed the color so you can see, instead of, if light just got cut off, then by the wall here, then we would just have parallel sound waves coming out. But because light diffracts and it bends around, then you can hear away from just the straight doorway. The most famous diffraction thing is Young's double slit diffraction experiment that proved that light is a particle because of the way the interference happens. And so light hit two slits, and because of the diffraction, the light bent like this, but it created an interference pattern on the wall. These are called fringes. You have bright light, bright spots, and you have dark places. And the number is the order of the fringe. You have the central bright spot, and then the first order fringe, the second and the third, and then you have the central dark spots and the first order dark spots, and so on. And the equation that you need to know is that the distance between the slits is equal to the sine of the angle made to, if here is the center of my slit and here's where my bright spot is, it's that's the angle that we're talking about. And this should be a theta. The angle that the fringe makes with the line from between the slits to the screen, so it's this angle right here. And m is the order, so it's 0, 1, and this particular, it's m some places and n's other places. So in this diagram it should be m because that's the way the equation is presented in your course content, times the wavelength of light. This equation for dark lines becomes m plus 1/2. And so it's just a plug-in. Just you're going to be finding the angle, or you're going to be finding the order, or the wavelength, or the distance, given the other three things. If it's finding the dark lines, then it's not m right there. The equation would be d sine theta equals m plus 1/2 times lambda. Okay, and we are done with this, and I appreciate your attention, and I hope you found it helpful.